Look at this equilateral triangle with a perfectly inscribed circle. Finding its exact size is a classic challenge. To find that radius, r, students often fall into a trap, trying to brute force the geometry or memorize a rigid equation. There's a much cleaner approach. It relies on a simple mathematical trick, calculating the exact same area of this triangle in two completely different ways. Learning how to set up this double calculation gives you a universal tool. Once you understand the mechanics of the process, you don't need to rely on rote memorization. Let's find the baseline area, 1/2 base times height. For side S, drop in altitude h. The Pythagorean theorem isolates h as s root 3 over 2. Plugging this in, the total area is s squared root 3 over 4. Lock that value in. That equation represents the total absolute size of this shape. No matter how we slice or divide the triangle next, the total area cannot change. Bring back the inscribed circle. To find its radius, we need to shift our perspective and look at the triangle from the inside out, starting directly from the center point O. If we draw straight lines from that center point out to the 3 outer corners, we fracture the large shape into 3 distinct internal wedges. Isolate just the bottom wedge. To calculate the area of this specific piece, we have to find its exact height. Because the inscribed circle perfectly touches the outer edge, the radius line dropping from the center meets the base at a perfect right angle. That radius acts as the precise altitude for this small subtriangle. With a base of s and a height of r, its area is simply 1/2 s times r. Now click the 3 internal pieces back together to reform the complete equilateral triangle. Think about the algebra here. We already know the total area of the shape from our first calculation. How do these 3 identical pieces relate to that original number? The combined area of our 3 slices, 3SR over 2, must perfectly equal the total classic area we calculated earlier. Set the 2 expressions equal. By moving the terms across the equal sign and multiplying it out, the s partially cancels, the constants simplify, and we isolate our target. The radius r equals s root 3 over 6. Look at the physical geometry hidden in that result. Our total height h was s root 3 over 2, and our radius is exactly 1/3 of that. The center of the inscribed circle sits exactly 1/3 of the way up from the base. This diagram illustrates why the process matters beyond perfect symmetry. Look at this messy, scaling triangle with uneven sides, A, B, and C. The exact same inside-out slicing method works. The central radius still drops down as the right angle altitude for all 3 internal wedges. Adding those wedges together gives 1/2 AR plus 1/2 BR plus 1/2 CR. We can just factor out the common 1/2 and R. Notice what remains inside the parentheses. The sum of the bases is the perimeter of the entire shape. Total area always equals 1/2 the perimeter times the inradius. By mastering the process of equating areas, rather than relying on a rigid equation, you build a structural understanding that lets you solve for the center of any triangle.